Howdy, and welcome back again to my lecture series on introductory astronomy, specifically for my course ASTR 103 Astronomy Spring of 2022. What I'd like to do with this lecture is finish off the outer planets. I noticed with my lectures I'm starting to get a little bit, I'm starting to mix subject matter, and I'd like to keep the lectures subject matter contained. If I'm going to talk about the outer planets, I'm just going to talk about the outer planets. So this lecture is going to be unlike my. If I stop talking, then this lecture will be fairly short, or at least shorter. Oh, and congratulations to my friend John. Just found out he got tenure. Anyway, introduction to Saturn. Saturn, the second largest planet in the solar system. It is very similar to Jupiter, but there are a couple of key differences. The primary of which is obviously it's less massive, but it has a much higher rotation period. Its rotational period is around 10 hours, which means that it is far more oblate, and also the centrifugal force, or basically the centrifugal force, causes the surface gravity to be far less than one would expect for a planet of its mass, and so therefore its density is also far less. As I may have mentioned in previous lecture, its density is significantly less than 1. It's around, if it's significantly less than water, which is about 1 gram per cubic centimeter. Saturn's density is actually about 0.7 grams per cubic centimeter. So again, if you have a large enough bathtub, Saturn would float. Obviously, the most recognizable feature of Saturn is its rings, which we'll talk about momentarily. And the rings are a beautiful, extensive ring system, and they're very curious in that there are a few features about the rings that we don't fully understand, particularly their longevity. Now, when we look at the structure of Saturn, is very similar to that of Jupiter, but because the mass is slightly less, it lacks a few, some of the regions are a little bit less. But generally speaking, what you have is you have an upper atmosphere of that is banded due to the shearing of winds from left to right and right to left. Beneath that, you have a mantle, as it were, of molecular hydrogen, followed by a liquid metallic hydrogen underneath it. You also have some minor constituents of hydrocarbons, and then beneath that you have something of a rocky core. Now, where Saturn differs from Jupiter is that, as I mentioned, there is banding patterns across Saturn, but it is much more muted than you see with Jupiter. They don't seem to be nearly as prominent. And the reason for that is because Saturn is colder, we believe that there is essentially a smog or a haze which has enveloped the upper atmosphere, and it's causing the banding pattern to essentially be muted out or hidden. And what we've found with satellite imagery, or satellite mainly spectroscopy, is that deeper down, the banding is there. It's just not as we just can't see it visibly because of literally it's got too much stuff in the way. I call it smog. Other people call it haze, but essentially it's the same idea. It simply just masks our view of the atmosphere further down. Now, Saturn does have a significant magnetic field, but it is not nearly as significant as Jupiter's, and we believe that it is caused by the same mechanism of liquid metallic hydrogen rotating very rapidly around a core of rocky material. Now, because again of the lack of mass, or the smaller mass, we do not believe that the liquid metallic hydrogen is nearly as extensive, and thus, since there is less material to create the dynamo, there is a smaller dynamo, and hence a smaller magnetic field. As I mentioned, the Saturn's rapid rotation is around 10.6 hours, is one Saturnian day, and you can see just how oblate that makes the Saturn's how oblate that makes the Saturnian shape. It's not a perfect sphere by any means. It is much more extended at the equator than it is at the poles. Now, with that red circle is to guide your eye, but many people believe that it's, or see Saturn as oblate, more oblate than it actually is, and that's just simply an optical illusion of the ring system. And as I said before, it is that rapid rotation is what contributes to the low density of the planet. Because Saturn is cooler, as I mentioned, there you have the upper atmosphere of this hydrogen haze, but beneath it and beneath a layer of methane, you have this ammonium sulfide, hydrosulfide in water. Again, very indicative, or basically the same as you see on Jupiter. It's only because of that upper hydrogen methane layers that we cannot see the banding nearly as distinctly as we can with Jupiter. Saturn, though, has enormous wind speeds because, again, while for two reasons. One, it has a significant energy source, which I'll talk about in a moment, that is not simply just due to gravitational contraction. So you have more energy to work with, and it's naturally just rotating faster than it does, say, for example, Jupiter does. So you can have enormous wind speeds of around 1,800 kilometers per hour, which are significantly, about 5 times faster than those you see that we see on Jupiter. And again, there's significant shearing. Some of the bands go one way, go east to west. The band right above it goes west to east. And that also creates storm features, such as the northern and the southern poles. Now, the southern pole really just looks like a hurricane. It's kind of a great red spot. Apologize for that. Judging by that, it's probably Robo calling me. I keep telling him that we're done, but he never listens. Anyway, the southern polar storm, basically a big hurricane. You can see it's somewhat similar to the Great Red Spot, although that image is more red than you would see visually. This image was taken in the infrared part of the spectrum, so it's false color. But the more peculiar one is the northern polar storm, which is hexagonal in shape. And so, which wasn't quite known as to why that was the case up until fairly recently, within the last decade. Astronomers really didn't have a very good grasp of what was causing that. And now we believe that we've been able to model, using the jet stream as our own jet stream as something of an example. We know that it may be due to, or we believe that it may be due to, just a complicated wind structure where you have these various high-speed winds interacting with each other, not in a direct sort of way, and they're not all traveling in the same way. So it's a much more complicated flow, and we have this hexagonal shape as because of it. Now, I mentioned there is another energy source instead of just gravitational collapse with Saturn. So a great deal of energy that Jupiter produces, more so than it gets from the sun, is because the planet is currently still compressing, which changes potential energy into heat. With Saturn, because of its lower temperatures, helium is actually able to condense into liquid. And so this liquid is more dense than the surrounding gas, and it rains through the atmosphere. And as it does so, very much like differentiation did for the Earth and the terrestrial planets, this rain creates friction, and that friction generates heat, and so there is more energy production in Saturn than you ordinarily would expect, even with gravitational contraction. So it's one of those that I don't know why, but I always find it just fascinating that there is rain inside a planet, and that rain happens to be helium. So I just try to imagine that, and it's I don't know, it tickles me. And so Saturn has, at the moment, 82 known moons, while the while for a while there, we were getting almost daily updates of the number of exoplanet systems that we were looking at. When I was coming up, it was almost the same thing with Saturn and Jupiter. There was this running competition as to how many moons these worlds actually had. We'd find a couple every couple months or every year or so. But Saturn seems to have really won this competition with around 82 known moons to Jupiter's 60 some odd moons. And these are divided into regular and irregular satellites. And this classification actually covers all Jovian planets, but really with Saturn you can see it more prominently. Regular satellites are satellites that rotate and revolve in a prograde way, meaning that they do so in the same way that Saturn rotates and revolves, counterclockwise as viewed from the north. The irregular satellites are those that rotate in the opposite way. They rotate and revolve in a retrograde manner. They are also tend to be higher in orbital eccentricity. Their inclinations are also higher, and they are definitely at the edges of Saturn. So what we believe happened here is that the regular satellites more than likely formed with Saturn, kind of in a analog to the solar system. You had the planet condensed from the medium, from the disk, and because of that rapid rotation that occurred, you actually had a smaller disk of material, a proto-lunar, as it were, disk, and then from that disk of material, the regular moons coalesced. The irregular satellites, we believe, are very much like Mars, are captured asteroids, or possibly from the belt, or just capture debris from the remaining material from the solar, the protoplanetary disk. The two most interesting of these worlds, or at least the two most peculiar, depending on, interesting is a poor word in my example because it's very, very subjective. Anyway, the two most focused on, I should say, moons are Titan and Enceladus. Now, I do have an errata to make for my previous video. In the previous video, I mentioned that there were geysers on Europa, and that a satellite passed through them and was able to detect elements for life. That actually, I got that confused. That scenario is on Enceladus. While there is active cryovolcanism on Europa, it is the geysers on Enceladus that lead us to believe that there is possibly life in these subsurface oceans within those worlds. Enceladus is very much like Europa. You can see it on the left there. It is essentially a frozen world. There's I wouldn't say very little cratering, but there is less cratering than you would expect, simply because of the fact that the surface gets resurfaced because of this cryovolcanic action. Water from beneath swells up to the surface and then flows out and obliterates any evidence of cratering prior to the volcanic activity, and quickly freezes into the surface. So Enceladus, because of potentially because of tidal forces between either it and Saturn, and it and another moon known as Dione, we believe very much like Europa, there is heat there, and so it has created this water mantle. And again, we have seen these elements through Cassini, passed through one of these geysers, picked up all of these elements that we know are necessary for life, and so we believe that Enceladus is yet another likely place for life to exist. Now, the world that I like to refer to as Bizarro Earth is Titan. Titan, if formed away from Saturn, if it had formed in the solar system by itself, would be a planet in its own right, because it is larger than Mercury. Now, because it has a significant amount of mass, it is the only moon to have an atmosphere a substantial atmosphere. In fact, the atmospheric pressure on the surface is about 1.5 times the surface pressure of the Earth. So it has a substantial atmospheric pressure. And the atmosphere of Titan is very much like the Earth's in that it has a tremendous amount of, it's primarily composed of nitrogen. However, it doesn't have any oxygen, and I blame the fact that it's too cold for plants to have lived or developed on Titan, because a lot of the oxygen that we have in our own atmosphere is due to plants being a thing. So you have a massive, or you have a substantial nitrogen atmosphere. You have it's cold enough that some of the nitrogen, some of the elements within some of the hydrocarbons within the atmosphere, like ethane, methane, acelytene. I can never pronounce that properly. Anyway, hydrocarbons will actually condense in the atmosphere and rain down onto the surface of Titan. So you not only have an atmosphere, but you have precipitation, and this precipitation acts very much like it does on the Earth. It hits the surface, which have mountains primarily composed of water ice. It flows down these mountains, creating rivers and channels, and then flows into lakes, such as the one that you see here. This is one of the lakes on Titan, and it is primarily composed again of liquid methane or hydrocarbons, and it looks very oddly or eerily similar to Lake Mead on the Earth. And so you can see those the kind of the lines running through it of the river, what appear to be riverbanks or the river delta for this particular object. You have islands within the lake, and so yeah, I recommend looking at this with in comparison to lakes on the Earth. Now I want to show you a video that was put together by NASA JPL, and if I remember which video I'm about to show you, assuming YouTube allows me to, this is all actual footage. This is not a simulation. This is actual footage from when the Huygens probe deployed from the Cassini satellite and actually went down to the surface of the world. And one of the things that I love about this particular mission is that they actually made Huygens, I was going to say floatable. It has the ability to float because they knew they highly suspected that there were bodies of water, or bodies of liquid methane. So they wanted this probe to be able to land and not sink down into a lake. So they made it so that it floats. So here, let me play this for you. This is obviously a simulation. This is not. So these features are very reminiscent of mountain ranges that you would see on the Earth, and they are due to similar geologic features that you see on the Earth. Particularly, you can see these drainage channels along the mountainsides. quick edit. And then we have these smooth rocks that, again, best explanation for why they are. Oh, here's the parachute. Why you have such smooth rocks is, again, weathering due to a liquid material. I think they overestimated the actual smackdown on that animation, but there you go. So again, I mentioned Saturn's moons Enceladus. It is small, but again, surprisingly active. It has geysers of water vapor and various different chemical components, carbon, potassium salts, things of that nature. And like I said, Cassini was able to pass through them, and leads us to believe that there is a strong possibility that life could exist in those oceans. As I hopefully mentioned before, we believe those oceans arise from tidal forces from Dione and potentially Saturn. Then we come to the rings of Saturn. All giant planets have ring systems. Saturn's is the only one this vast, this large. We believe that some of the rings did actually form at the same time as Saturn, but we also believe that some of them formed later on from rocks or material that got destroyed due to the heavy gravitational influence when you get closer into the world. As you get closer into the world, you will encounter something known as a Roche lobe, and at that point there is significant tidal stresses acting on any kind of body that moves into it, and depending on the structure of that body, they could get ripped apart. One of the most extreme examples of this that you might have seen is around the mid to late 90s. There was this comet by the name of Shoemaker-Levy 9. It was a comet, a single comet, that on its first approach basically went past too close to Jupiter, or passed within the Roche limit of Jupiter, and broke up into a dozen or so smaller cometlets. And then as it went around in its orbit, it came by and it literally machine gunned the surface of Jupiter and created quite a light show across the surface. And then we also believe that some of the rings on the outer edge were actually composed, or not outer edge, some of the smaller rings, in the inner edge, the E ring specifically, these were created via outgassing from Enceladus. Now, all of this material is almost exclusively water ice, with some contaminants of rocky material, again from either collisions off of moons or things breaking up in the Roche lobe. Now, the reason why the rings exist as rings and not some kind of diffuse cloud or what have you, and one of the reasons why they have lasted so long, is that they have, because Saturn has so many moons, a number of these fall into a category called shepherd moons. And these create I should first start off by saying that the rings, as you can hopefully see here, are not monolithic. It's not like a record player with that's a solid disc with grooves in it. And actually, the disc of Saturn is made up of thousands of tiny diskless or very thin loops or discs or rings. That's the word I'm looking for. Like you see here, and that's because these are held together gravitationally via these shepherd moons. You have, for example, Prometheus is shown here. Its sister moon is Pandora, which is on the opposite side of the ring, and because of gravitational influence, it's the pulling. If a moon or disk material decides to run away, one of the moons pulls it back in. If some of the material tries to dive into Saturn, then the other moon will pull it back in, and so it keeps these rings very tight and very organized. They also have an opposite effect in that they create gaps. And again, I'll come back to here. We have two fairly significant gaps. We have the Cassini division, which you can see even through a modest-sized telescope or a very good set of binoculars. And then you have the NK division, which is kind of a competition among citizen scientists whether or not if your telescope is good enough to be able to resolve the NK division, which is in the outer part of the A disk. These divisions, again, are caused gravitationally. They have certain moons, instead of keeping the material constrained into these ringlets, they push the material out and create these large gaps that we see. Cassini and NK are the largest of the two, but there are a number of other gaps between them. So let's move on to Uranus and Neptune. These are the ice giants, but again, as I always like to state, they are primarily composed of hydrogen and helium. They are just smaller sort of versions, smaller, colder versions of Jupiter and Saturn. And the cold is significant and is basically what really causes these worlds to be known as ice giants, because you have hydrocarbons, methane, ammonia, water. They exist in this, can exist in a large slushier way. You have a lot of these ices that are contained with them. They are also fairly rapidly rotating and can have storms in them. Now, like you can see with the Great Red Spot. The Great Red Spot was first imaged by, I know I'm going to get it wrong, Voyager 2, if I remember correctly, when it passed by. And really, these are the only images that we have of these two outer worlds, because we really haven't. New Horizons, I don't believe New Horizons went close enough to them to get any good images. So the only satellite that has been anywhere near these two, it was Voyager 2 back in the 70s and 80s. The reason why they're blue or teal is because of the amount of methane that they have in their atmospheres. The reason why Neptune is bluer is because it has more methane. It's colder, and so methane ice can freeze. You have more methane ice in it than you do in Uranus. One thing I want to say about Uranus and Neptune is their discoveries. Uranus was discovered. These are not naked eye planets. You need a pair of binoculars or a decent sized or a modest sized telescope in order to view them. Uranus was discovered by William Herschel, and he initially wanted to refer to it as he wanted to call the planet of all things George, after King George III. Love him, squeeze him, whatever. I personally think, and then the astronomers of the day overruled him and basically named it Uranus. I think there were a few Americans in this, because the quote-unquote proper pronunciation is Uranus, and so I think that was slightly a jab at George, but I could be completely making that up, but it's something I choose to believe. But Neptune is significant in that it is a great example of the scientific process. When Uranus was first discovered, obviously it was very well studied. People wanted to know what its orbit was like, and when they studied its orbit, they noticed there were some discrepancies. It seemed to slow down and speed up at certain points in its orbit. It wasn't a, shall we say, completely stable orbit. The most likely explanation for the oddities or irregularities in the orbit come from, or due to, there is a gravitational mass pushing and pulling on it, affecting it in some way. And they were able to determine, based on this, that there needs to be a planet that's further out, and they were actually able to predict where it would be located at a future date. And they made those predictions, and they trained their telescopes, and lo and behold, they found it. And so Neptune was first hypothesized based on observations of Uranus, and that hypothesis was confirmed via observations using the predictions from models. Now, the structures of these worlds, you have These, again, are composed of primarily hydrogen and helium, but the moons are not moons. The worlds are not massive enough to have a metallic hydrogen within them. There may be some liquid hydrogen within them, but it's primarily just molecular. So without the liquid metallic hydrogen, these will not have nearly the extensive magnetic fields that Jupiter and Saturn do. But I'm going to get into that in the next slide. So you have a molecular hydrogen sort of upper mantle, and then beneath that you have a slushy material of slushy ammonia, methane ice, liquid hydrogen, and so forth. And then above that you have dense rocky cores that are about the size of the Earth, but have much higher, as you might imagine, a much higher surface atmospheric pressure. Now, in terms of the magnetic fields, again, Jupiter and Saturn's are very well behaved, as it were. Saturn's is so well behaved, it's actually a puzzle as to why there is no deviation between the magnetic axis and the rotational axis, as there is, say, in Jupiter. Uranus and Neptune's way different. They are weaker, as I've said, but not only are the axial tilts, the magnetic pole or the magnetic axes, very much offlined from the rotational ones, they're also off-centered. They are not the dynamic or the magnetic dynamo creating these magnetic fields isn't around the core as it is with any other world, Earth, Jupiter, Saturn, what have you. And so the best explanation we can come up with is that there is some kind of circulation of ammonia ions, or essentially you have an ammonia atom, or ammonia molecule rather, and there is sufficient enough energy to knock off a couple of those electrons. So you have this positively charged ammonia molecule swimming around, and for whatever reason there may be these currents in the interiors of these worlds, which is causing these ions to flow in a roughly circular pattern or so somewhere within the Uranus, but they're not doing so around the core of the world. Why they are doing this? Very much of an open question. And hopefully we'll send more probes out and we can get more information as to, and we can solve this particular question. This lecture brought to you by the greatest Scottish restaurant, McDonald's. As to terms of their atmospheres are again not very complex, very much like Jupiter and Saturn. Primarily, again, composed of methane and ammonia, and you have very similar temperature profiles where diving into the world, from a sort of edge of the atmosphere, as it were, as you get deeper into the world, the pressure builds and the temperature builds. But you get to a point where the atmosphere is, and so as you go up, the temperature decreases. But then you get to the point where the atmosphere is rarefied enough that it's receiving a great deal of solar energy, and that drives the temperature up as you continue to increase in altitude. Now, going back to the colors, the reason why these worlds are bluish and teal shape is because methane is really good at absorbing red light. So you have blue light, which is reflected off. So you have white light that hits the world, the methane absorbs the red part of it, and then the blue part gets reflected back off. Now, in terms of the formation of the ice giant rings, and to a certain extent Jupiter's as well, is we believe that these are due to capturing of asteroidal material, or possibly cometary material, and that material wasn't captured in a stable orbit or any orbit whatsoever. It actually fell into these worlds, passed through that thing I refer to as the Roche limit, and they got spaghettified. They got stretched out to the point that they collapsed, or they got ripped apart. And that material then got gravitationally captured into a stable orbit and created these rings. In terms of something I failed to mention with Saturn and but this reminds me of it, is there is a certain open question as to the longevity of these rings. Given what we know of the amount of radiation that these rings, particularly Saturn's rings, which are primarily icy, given the amount of radiation that these ring particles are experiencing, we wouldn't expect them to hang around very long. We'd only expect them to hang around on timescales of hundreds of thousands of years. So, where do they come from? What keeps supplying it? Why is Saturn's ring so dense? The outer ring, the inner ring, I don't know why I keep getting that confused. The inner ring, E ring, we do believe is constantly being resupplied via Enceladus's geysers. As to the outer ones, again, open question. So yeah, astronomers, we don't know everything. Some of us like to think we know everything, but we really don't. So the rings of Uranus and Neptune, we believe, are actually more rocky material and were formed primarily from asteroidal and some cometary material. These are, because the radiation is not so high, we expect these rings to last for a longer period of time, but they're not nearly as extensive as Saturn. With the Saturnian rings, depending on what actually keeps them there, which provides their longevity, they may have formed with Saturn. There wasn't enough material around Saturn as it formed to coalesce, so the material coalesced in rings, kind of like the asteroid belt for the solar system, kind of an asteroid belt analogy or analog. Or, like I said, it could be something else related to how they actually hang around. These rings, all of the rings of Uranus and Neptune are within the Roche lobes of these worlds, and so all of the ring material is thought to be from outside sources. I've mentioned this a few times already. Uranus's rotation is wonky. It is knocked over to the point that its axial tilt, the Earth's axial tilt is 23.5 degrees. Neptune's is around 28. Well within the range of what we see with other worlds. But Uranus is at 98. Best explanation we got for this one is that it was smacked into at some point. Now, oddly enough, or weirdly enough, the rings around Uranus are also inclined at that 98 degree, and so are the moons. So are the regular moons around Uranus. So whatever collision happened must have happened very early on in the lifetime of, or in the formation of Uranus. The puzzle comes into how likely this is that such a large planetesimal was in such a rarefied part of the disk. We wouldn't think it'd be, if it is a collision, then it was really statistically improbable. Because of the high obliquity of Uranus, it has the most extreme seasons of any planet in the solar system. It's actually its orbital period is so long, and we've only known about it for such a short period of time, and its actual obliquity is so large that we've only been able to study one half of Uranus. We actually haven't been able to see the other half of Uranus from the Earth yet. Maybe after, as you can see here, in 1986 we saw the front of it. In 2028 we'll see the back end of it. And so we really haven't been able to study it in any great detail since then. We have for example, we have an incomplete wind record. We know what the wind speeds are on one hemisphere, but we don't know what the wind speeds are like on the opposite hemisphere. In terms of climate, as it were, one half of one hemisphere gets sunlight. So in the summer months, the sun never sets for the northern hemisphere, as it were, and for the winter months, the sun never rises for an entire hemisphere, unlike what you see on the Earth. In terms of Uranus's moons, the one that's most peculiar is Miranda, as seen here. With these worlds, with these moons of these outer planets, because they are so much smaller and because they're cold, we do not expect them to be overly geologically active. We expect them to be essentially just rocks that are cratered. But with Miranda, we had just a smorgasbord of geologic features. We have canyons, rents, things that you can see there. A lot of the stretch marks, as I like to think of them. Now, one of the explanations for why this, or the main explanation for why Miranda is the way it is again, ye old tidal forces. But in Miranda's case, it may be that that the tidal forces were so extreme that not on one, but on multiple occasions, Miranda was ripped apart and then was able to gravitationally reassemble itself. And so that's why the moon is so almost pockmarked, as it were. Neptune's largest moon is Triton. It is the only planet that is in a retrograde orbit. This is again highly irregular, simply because it is a substantial moon. It is spherical under its own mass, and so because it is in a retrograde motion, we again believe that this is a sign of gravitational capture. Now, with Mars and with Jupiter and Saturn, the regularly shaped moons are basically gravitationally captured. We believe those are small, they're potatoey, so forth. Triton is not small, and it's certainly not potatoey. So again, from a dynamical standpoint, it's highly unlikely that this is going to occur. Obviously it did. So it's one of those 1 in a million kind of, or more, lottery sort of odds in capturing. So it's peculiar, at least in my mind, that we have a number of lottery winnings, as it were. We have the retrograde of Triton, we have the axial tilt of Uranus, we have the axial tilt of Venus, and so a lot of and we also have our moon. So there's a lot of, shall we say, unlikely events that have actually occurred within our solar system. But I digress. And so there is a lot of cratering that is on the moon, as we can see. But there's also this cantaloupe sort of terrain, and very much like a lot of the moons that I've discussed, we believe that there is a significant water ocean beneath it, or liquid ocean beneath it. And so in this case, it's not water, it's actually nitrogen. And so the nitrogen spews out from cracks due to tidal stresses and creates a very thin veneer of a nitrogen atmosphere, but it also creates this cantaloupe sort of terrain where the nitrogen slumps out from these geysers and then freezes very quickly, and it causes this dimpled sort of features on it. And with that, I will end my discussion of the Jovian worlds and their moons and their rings. Again, as always, I hope that you found this entertaining, and definitely I hope you found this to be educational. Next time, I believe I will be talking about the sun, but don't hold me to that. I really should know what I'm going to be talking about next, but I like to keep things fresh. I like to keep, variety or surprise is the spice of life, or something like that. Anyway, I hope you all have a great day, or night, or what have you, and peace out, and I will see you all next time.